we've talked so far about solutions and how to correctly make a solution. Now we're going to talk about dilutions. Do you know what dilutions mean? What does it mean what's it mean to dilute something? Right, dilution means that we water it down, basically. Right, we water it down. Usually, 99.9% of the time, dilutions are made with water. You could technically dilute solutions with whatever your solvent is, right? If your solvent is not water, you would dilute it with whatever that solvent is. But dilutions are taking a solution and reducing its concentration, right? That's what we're doing, reducing the concentration of a solution by taking a little bit of the concentrated one, putting it in a new container, and then adding whatever your solvent is to kind of thin it out. Are we envisioning what's happening here with dilutions? Yes. Okay, so it's like taking out a little, dropper of Kool-Aid and putting it in a gallon of water, right? It's barely Kool-Aid anymore, right? It still is a little bit, but it's got a really, really weak concentration. So when we make dilutions, we start with what are called stock solutions. Stock solutions are like laboratory grade, like purchased solutions. So when I buy solutions for our labs, they come at an extremely specific concentration. I can buy them at 1 molar or 10 molar or 20 molar or whatever I might need. But I buy that stock solution. And then whatever solution we need to use for our lab, I'll make it based on what the concentration needs to be, right? If I buy it at 1 molar and I only need it to be 0.5 molar, I put in half of what I need, fill it up with the rest with water, right? And I've got my concentration to be what I need. But that's how it works when we buy solutions and how we get different solution concentrations in our labs. We're going to be able to calculate how much stock solutions we need and how much different, how we can make dilutions of solutions using this equation here. C1 times V1 equals C2 times V2 is the equation that we need. What do you think the C and the V probably stand for?
Concentration, volume.
Concentration and volume. Okay, sometimes you'll even see it written as M1 V1 equals M2 V2. This would stand for like molarity. Okay, you can see it written like that as well, but usually I was taught C1 V1 equals C2 V2, so that's what you'll hear me say the most often. But it just means concentration. If you notice, if we're talking about concentration in molarity is moles per liter. We need to make sure that our volumes are consistent units. They don't necessarily have to be liters, but they have to be consistent units on both sides. I think it's most applicable when they're liters, but it's probably not the end of the world if they're not. So I'm going to probably get us into the habit of making sure we are in liters when we put in our volume here. But that's just something I want you to be aware of. It's got to for sure be consistent on both sides.
Wait, so as long as this, that's what we use then?
That's okay. I would still strive to just put things in liters. That way you know it's going to be good. But in all reality, you would do the math the same way on both sides, so it would cancel out. But I'm just, for ease, we just put it into liters. Okay. We need 500 mils of a 1 molar acetic acid solution from a 17.4 molar stock solution. What volume of the stock solution is required? Okay. You have to be pretty good at using context clues here to figure out which sets of my information go together, right? One is concentration and volume of the stock, and one is concentration and volume of the dilution. So we've got to be able to pick out which of these things need to be paired, right? Sometimes that's the trickiest part. So I need 500 mils of a 1 molar acetic acid solution, so that has to be a pair. Right? It makes no difference which one you call 1 and which one you call 2, right? That really makes no difference. Which one goes on the left of the equal sign or the right of the equal sign doesn't make a difference. So I need 1 molar times 0.5. And to get that, I use a concentration of 17.4 molar. And the question is, what is the volume of that we need? Right? Do you see how that works? I'm looking for volume of my stock solution in order to make this over on the left. Okay, so I'm going to take 1 times 0.5 divided by 17.4, and I would get a volume equal to 0.0287 liters, because I put this one into liters. And if I wanted to go back and kind of match my original and to really compare with that, I would say I need 28.7 milliliters of my stock solution.
Do you have to do that?
You don't necessarily have to. It might ask you specifically what volume in milliliters or whatever, but I'd probably take either answer there. Okay. But this gives you kind of a frame of reference as to if I want 500 mils and I'm only putting in 28 mils of my stock solution, that means the rest of it is just water, right? So you're really watering that down to go from 17.4 to just a 1 molar solution. Do you see how that works? Pretty simple math, right? The math is straightforward. The tricky part is figuring out which sets of this information kind of go together.
Yeah, so just understanding the context of
Yeah, that's exactly right. Right.
So what does the 28.7 milliliters represent?
This tells us how much of the stock solution we would have to put in to a new container. Then we would fill it up to 500 mils.
Okay.
Right? So we drop in our new one, then we fill it up. So I want us to watch a little video about how to make a dilution. Now that we kind of know the math that goes behind it, I want us to watch. I've got a video here about how to make a dilution, so I want to show that real quick.
An assistant professor of chemistry at Elon University. Today I'll be taking you through the appropriate procedure and technique for diluting a solution. A common laboratory technique is preparing a more dilute solution from a concentrated stock solution. In this case, we are going to prepare a 0.250 liter solution of 0.01 molar. We know our stock solution has a concentration of 0.250 molar. The first thing we need to do is determine the exact number of moles in our dilute solution. We know our concentration needs to be 0.01 molar or 0.01 moles per liter. Since we know our number of moles per liter and we know the volume we need, we can calculate that we need exactly 0.0025 moles of sodium chloride. Knowing our stock solution contains 0.25 moles per liter, we can take the number of moles needed in our dilute solution and divide by the concentration of our stock solution to calculate the exact
He broke
number
it down
of milliliters
further than we
that
need
must
to,
be
right? We just
transferred
use
into our
C1V1
new
equals
solution.
C2V2. So he
In
broke
this
it down
case,
more
0.01
in more
liters
math than we
sodium
really
chloride
need, but
solution,
whatever.
or 10 milliliters. This is the stock solution of sodium chloride that we will be diluting. Make sure to pour the stock solution into another container before inserting the pipette into the solution. This is because you do not want to contaminate your stock solution. In this case, I'm using an Erlenmeyer flask. Notice that I have clearly labeled the...
Okay, so do you see what he's saying there? So if I was going to make a solution for us to use in the lab, I would never put my pipette into the bottle that was mailed to me. You know what I'm saying? I would never put my pipette into that bottle. I would pour it into another container, use the pipette to do what I need, and then whatever's left in that little other container, it has to be disposed of, right? It can't go back into that stock solution. That's really important. Do you remember why? It will contaminate that whole solution, right? If I accidentally had water in my pipette and moved it in there as I was drawing out some of that stock solution, then now my concentration is not what it says it is. It's probably really close, but it's not exactly, right? Last year in this class, I was trying to do the lab that we're going to do later in this chapter, and all of our concentrations were coming out twice of what they should have been, but that's because I don't know how old the stock solution was, and I don't know if someone else messed with it, right? It was here when I got here, and all of our calculations were way off. So this year I ordered new stock solutions, hoping that that was the issue that we ran into, because I didn't know if that stock solution had been tampered with. And so I trusted what it said on the bottle, and all of our calculations were like double what they were supposed to be. So I have no idea what happened with that. So it's good to make sure that you have those things removed from their original.
to adhere to proper laboratory safety protocol. To prepare our dilute solution, we will take a 10 milliliter aliquot of our stock solution using a 10 milliliter volumetric pipette. To use the pipette, place the pipette in the liquid to be collected. Squeeze the pipette ball and allow the liquid to rise up the pipette. You should allow the liquid to pass the line marked on the pipette, but before the ball. Remove the ball and place your other thumb over the end, creating a seal, and slowly release just the corner of your thumb, allowing the liquid to exit so that the meniscus is directly on the line marked on the pipette.
Okay, so that's called a volumetric pipette. You see how the meniscus is super clear there? And that's kind of interesting. You've got a really, really small opening within that volumetric pipette, which allows for a lot of that surface area and that surface tension to kind of grab on there. So you see a really, really clear meniscus, which I think is interesting. We will use these volumetric pipettes. They have a bulb and a bulb control that allows it to draw liquid up and draw liquid back down or release liquid back down. But yeah, we'll use one of those volumetric pipettes.
Some practice, and you may need to use the bulb to pull more liquid into the pipette again. Never pipette by mouth. Once you have the exact amount of liquid required in the pipette, hold your thumb firmly over the end and transfer the pipette.
What's that glassware called? Volumetric flask. Good. Volumetric flask. Remember, there's just one line on the neck of it, right? So if we go over, we got bad news.
Metric flask. In this case, a clean 250 milliliter volumetric flask. Allow all of the liquid to flow out of the pipette. Do not use the bulb to force the liquid out, as pipettes are designed to deliver the exact amount of liquid, and there may be a small amount of liquid remaining at the end.
Okay, did you hear that? That's kind of interesting. When you use pipettes, these volumetric pipettes, the bulb suctions this liquid up, and then as you release it, they don't want you to like shake the liquid out of the pipette. It's like measured so that if there's liquid reserved in the pipette, like it's okay. It's kind of interesting, but you're not supposed to like shake it out or like try to really extract it out. If once you let it drain, then that's it. Don't like try to get all of it out. It's kind of interesting and kind of counterintuitive, really. But it's measured to like include that error.
Remove the pipette and follow the same procedure as before, filling the volumetric flask with solvent. Again, monitoring the meniscus until the exact volume is reached. You've now learned how to prepare a dilute solution from a stock solution. To see how to prepare a stock solution, you can view our...
What volume of a 16 molar sulfuric acid solution must be used to prepare 1.5 liters
of a 0.1.
Yeah, sorry, thank you. Of a 0.10 molar sulfuric acid solution. I was doing something. All right. So we need to see here. It says what volume of a 16 molar. So that means that has to be a pair, right? I'm looking for, if my concentration is 16 molar, what volume do I need to make 0.10 molar 1.5 liters? Okay, does that context feel fine? All right, are we comfortable with how that gets read and how we use that?
Yeah.
It doesn't matter if you have it as like V2.
Nope, it doesn't matter if this whole set goes on the left and this whole set goes on the right, as long as we don't mix and match them.
Cool. That's
Right.
what I did
Nope.
the other way.
It does not make a difference. So let's see
So-
here.
In this, like, when we're learning this, we don't really need to know about, like, the compound.
Yeah, good question. We don't play into. I mean, there could be a situation where it talks about grams and you have to calculate the molarity before it goes into the dilution equation. But for the most part, no. So that means I would need 0.009375 liters, and so that comes out to be 9.375 milliliters. Right, and I would take either of those.
Yeah. Would you most likely just keep it in liters because that's what it is?
You can.
Okay.
I just pressed the 0 on my calculator like 8 times. Thinking.
It should be. All these had 2, which means I should really have gone to 9.4 mils. Right. Yeah. Okay. All right. Why don't you try the next one here on your own?
Holy.
She said.
Who are you? Joseph.
And then
Who are you?
for that, could you also just put in milliliters?
If you wanted to leave that in milliliters, you could, because then your answer then would come out in milliliters. So either way is fine.
Like plastic ball for like
Okay.
metal.
What questions do we have about dilutions?
Feels pretty fun.
Pretty simple, right? Okay.
Snazzy
So your
things.
homework today has both solutions, which is just regular molarity, and dilution. So now you've got to be able to read context clues and figure out, is it a dilutions problem or is it just asking me about the concentration in one scenario, right?
Okay.
Dilutions kind of have a before and an after. Otherwise, it's just a regular molarity type problem.
Like what we did on the previous one.
Right.